Professor Lada, Professor Masha, and Professor Ekaterina, and there is one professor.
Olga. Her name is Olga.
Oh,
She's the
yeah.
professor. Yes, but actually me and Masha, we are not professors. We are just like managers.
Oh, okay. And Professor Olga never teach us?
No, she's just like manager.
Oh, okay. Yes. Okay. Thank you.
You're always welcome.
Can you hear me?
Yes, we can.
Okay. Okay, give me 1 second. I will start the presentation. One second. How can I share my screen? Okay. Okay, can you see my presentation right now? Can you see my presentation?
Yes, I can see it.
Yeah, I can see it.
Okay, good. So I can begin. Okay, my question is, how many of you are generally familiar with the metal forming? So
I had in the first semester of the bachelor, there was a bit about the elastic deformation and plastic deformation and the flowing and these things.
Okay.
But it's been a long time.
Okay, because today I'm going to talk something about metal forming, but it's not typical metal formings. Okay, just to show you, I will be also using this software to draw something because I think it's a good way to explain some things. So just give me 1 second. Actually, it was I thought that this presentation was about to begin 1 hour later, but never mind. Everything is ready. So generally, metal forming is used to produce some products, mostly that has some certain, let's say, function or performance. So we can, let's say, we can divide the metal forming. One of the division is primary division and secondary division. Primary division is usually used to make some semi-products like rods or some bars or some profiles, right? So you can use it for some other functions and other things. And secondary is metal forming is used to produce final parts. Let's say you want to produce, let's say, to make this wonderful car, right? And to produce some parts and other things. So severe plastic deformation is, on the other hand, is a little bit different, because the purpose is not to produce part that has some functions, but to improve the properties of the material. So today we are going to talk about, let's say, severe plastic deformation. I'm going to give you some introduction. Then I'm going to give you some history background. After that, we're going to speak something about methods. Then I'm going to mention several things that usually occurs with processing by severe plastic deformation. One of them is saturation effect. Then I'm going to talk something about upsetting or SPD processing by three-shape dies. Actually, that was my PhD thesis. So I'm going to give you the results of my research. Then I'm going to talk about application. Why do we use it and what for? And then finally, we are going to talk about the materials for SPD processing and the future of SPD processing. So I'm from Serbia. I'm not sure if you are familiar with this country, small country in East Europe. So it says here from Samara to here, maybe almost 8 hours by flight. I was born in 1979 in Serbia, and I served in several laboratories, different laboratories. So I have quite wide of the how to say wide employment in different laboratories, and finally I settled down in a laboratory for metal forming and laboratory for polymers. I did my PhD in severe plastic deformation, and I have extensive cooperation with the universities in China, Taiwan, and Japan. So I mostly do research with Asian universities. And my interests cover severe plastic deformation, cold bulk metal forming, friction in metal forming, microforming, workability in metal forming, and other things. And these are the classes I teach. It says here non-conventional metal forming. This is where severe plastic deformation, is for. Just note at the lower right corner, there's a slide number. So if you have some questions, you can ask me later. I will provide at the end maybe 10 or 15 minutes so we can have some discussion. Or if you have like a lot of questions, if you have something that is very unfamiliar for you, you can interrupt me and I can explain. It's no problem. So the name of this summer school is Space Materials and Technologies. And of course, I think severe plastic deformation will fit into this category, right? Also, I'm not familiar with how to say the structure of this presentation. Should I make some pause? Like, let's say maybe after 1 hour. I mean, what did you experience? How did the other presenters did? Did they make some presentation, some pause, or they just give presentation for full 2 hours?
I think most presentation that took 2 hours did like 5 minutes pause in the middle.
Okay. Okay. So we will make a 5 minutes pause after 1 hour. Okay. Here's the story. How actually severe plastic deformation started, and not just severe plastic deformation, but also how the engineers and researchers gain idea. On these two photos on the left, you can see some, it's SEM of some plant morphology. And actually scientists notice that, for example, lotus flower grows in the pond that is very dirty, right? But they figured out that the lotus flower is very clean. So they wanted to know how is that possible. And when they took the sample of the plant and took it to the microscopes and other devices, they noticed that these plants have, let's say, this kind of morphology that enables, let's say, to reduce the friction. So the lower the friction, the less chance there is for the, let's say, some dirt or some unwanted particle to stick to it, and then, right, it will just fall off from the plant, and the plant will look clean, right? And on the right side, there is the sample of the shark teeth. They notice sharks have very, how to say, strong teeth, and they realize that how to say, the structure, the micro, let's say, quotes like microstructure of the teeth is somehow like intentionally built in a certain way. So they notice that the core is very elastic. It can bend, and they realize that that's, let's say, this serrated surface is very hard. The higher the hardness, the higher resistance to the wear. So they realize, wait, like if the biology, if the organisms can, how to say, control the properties, we can do it as well, right? So we are focusing on the next. We are just focusing here mostly on the metals. So I'm not really familiar if the civil plastic deformation can be used for other materials, but we are just dealing here with the metals. So in these two photos, photo number 1, photo number 2, you can see relatively same size samples. So it's around 6 centimeters long and maybe 1 centimeter by 1 centimeter, right? In width and height. So what is the difference? Of course, material is different. His is a low carbon steel, and this is a sample made of vanadium. So you can just, the first thing you can notice is you can see actually in this left image, you can see the grains. So you can see, for example, this is one grain. Of course, I mean, I guess that this sample was properly etched, so intentionally, so we can see the grain. And the average grain size, it says, I don't know, it varies maybe from, I don't know, 4 millimeters to maybe 10 millimeters. And let's say that average grain size is 7. On the right image, you can see the sample, but the thing is you cannot see the grain size. Why? Well, because the grain size is around 19 micrometers, right? So you cannot see it. You need special, I mean, not special, you need microscope. So you can use like ordinarily light microscope. Of course, you can use SEM or others. So I just want to emphasize that the samples has different size of, let's say, building blocks. Okay, this is also titanium crystal bar, and you can clearly see the crystal, right? You can see the crystal grains. We call it the grains, but the full name should be, let's say, like crystal grain, or just one. We can say just one crystal. Let me just remind you that in each crystal, the arrangement of atoms is the same inside the crystal. So that's the difference between the crystal and, let's say, amorphous structure. So let's say if the atoms are arranged like this way, it will repeat, right, throughout the whole crystal. Of course, we have some defects. Nothing is perfect. Actually, one of the things is to say that these imperfections, let's say this atom is missing, or we have atom here, these imperfections made plastic deformation possible. If the crystals were perfect, then I just read in one book, they say metal forming might be impossible because we would need like 10 times or 100 times stronger machines, which is like impossible. Okay, I'm not sure if you are familiar with the Hall-Patch equations. Hall-Patch did one research, and they wanted to, they wanted to investigate what is the influence, let's say, this equation. This is, yes, it's not big D, it's small d. Average grain size, what it has effect on the yield stress. So if you have, let's say, this like flow curve, what is the effect of this point? And then when they did research, they realized the smaller the D, the smaller the crystal grains, the higher, right, the yield stress, and presumably the other performance of the materials. So it means that material, like roughly speaking, that material will be strong. So in these two images, it's actually the same material, is steel C45E. It's a low carbon steel. Low carbon steel, sorry. And this is, let's say, the initial microstructure of the bright drawn material. So this is ferrite and this is pearlite. Of course, depending on what background of material science and mechanical engineering you come, you will just have different understanding. Some scientists don't take account into, let's say, microstructure. For other people, it's very important. So I will just try to cover both, right? Both aspects. Ferrite constituent is more soft, pearlite is more hard. And this is the microstructure. As you can see, it's fairly uniform. You have the mix, and the let's say the shape is, you can say it's, let's say, ball shape. Has approximately ball shape. However, if we take this material and processing throughout drawing, rolling, or we do some compression, we do some setting, we will find in some very narrow layer, let's say this approximately this area, that the microstructure is vastly different. Actually, we cannot see, we are not sure what happened here. So if you zoom it further, you will see that in this layer, the grain size, or I should write, let's say, D, has dropped significantly. In the rest of the part, you can see here, this part maybe looks like a little bit like this, right? But in this narrow layer, the grain size has reduced drastically. What does it mean? So it means that in this layer, D will have improved properties. Okay, one thing to say, I'm not sure if you're familiar. Let's say if you increase in metal forming, if you increase, let's say, the hardness and the strength, the ability to plastically deform, we call it workability or formability or maybe malleability, I don't know which term are you familiar with, is dropped, right? So so it means like if, let's say, one property is improved, the other property will fall. So it does means that, right, this layer has improved most of the properties, not all, because we've seen some of the properties before. So scientists and researchers and engineers decided, okay, this is good. I want to have material that I will have with improved, that will have the improved properties. Why? Because usually more expensive material has better properties. It's not always the case. Or let's say if you use alloyed material, which is usually more expensive, or it will take you, how to say, it will have higher impact on the environment. It's usually right, it's more expensive. And then why cannot we just buy some cheap steel, improve its properties, and we will have the same properties like expensive material? That's why they made a special metal forming methods. It's called severe plastic deformation methods. We will see what is it about. Let me just check my timing. Okay, so I will just give you here the definition. Processing Processes of severe plastic deformation are defined as metal forming processes in which a very large plastic strain is imposed on a bulk in order to make ultrafine grain material. The other definition, it says that unique feature of SPD processing is that the high strain is imposed without any significant change in the overall dimensions of the workpiece. And another feature is that the shape is retained by using special tool geometries that prevent free flow of the material and thereby produce significant hydrostatic pressure. So we just see here that severe plastic deformation, among one things, is how to say, focus on the process, drawing, rolling, upsetting, and thing. So some people, once we become familiar with SPD, I'm going to explain other things. Okay, it says here, processing by SPD causes following changes in material: exceptional crystal grain refinement. This is very true, up to sub-micrometer or nanometer scale. Causes unusual phase transformation, introduce large waves of features, and you can read about this. And these changes offer new opportunities for fine-tuning the properties of SPD metals to achieve significant properties in their physical, mechanical, and chemical functional properties. So the main goal of processing by severe plastic deformation is material property. So material property is the main goal. It says here that with SPD you can get average grain size, let's say 100 to 900 nanometers, and we call this material ultra fine grain material. Just for your reference, let's say usually for metal forming, the average grain size we encounter is like between 10 and 100 microns. That's usually, of course, it's always higher and lower than that, but that's usually the average grain size we encounter. We also get improved material properties compared to materials processed by conventional metal forming. So conventional metal forming can produce SPD effect as well, but not in a controlled manner, and not, let's say, if you want to have, like you have this sample, or you say, okay, I don't want just to have SPD effect on this surface area. I want to have it in entire product. Of course, these are just definitions. Everybody has its own definitions, so we need to limit these, how to say, definitions to a certain manner. For example, alloy steels, which are usually expensive, can be substituted with the carbon steels. That will reduce the usage of rare metals and improve the environment. How did SPD started? It started long time ago. For us, it says that it started in China more than 2,000 years ago, and also in India. However, people knew that when they do something with the metal, they will get this SPD effect. But of course, at that time, they didn't have these proper microscopes so they can analyze. The first scientific reports by SPD was done by Percy Williams Bridgman. He received a Nobel Prize for his work. And then, let's say, he actually invented one SPD method, but he didn't utilize fully. We will speak about it later. And in 1988, it's the year that the first report, the first papers and general public start to have interest about SPD at the very this moment. It says in 1993 there was the first publication by international team, and as I said, these initial reports started to the interest of general public, research public about this. Okay, now we are going to talk about severe plastic deformation methods. The first and the most well-known is called equal channel angular pressing. Why it's called like this? First, you have two channels. You can see one channel here. I'll just draw one channel here, one channel here. So it's equal channel. The angular, because there is a certain angle between them, right? Here's 90 degrees, here's maybe 120. And it's called pressing because you put the sample that is, let's say, it can have this shape like this, and then you press it throughout this channel. Once you press it, it will pass through this intersection plane. You see, this intersection plane. Once it passes this intersection plane, you will impose certain amount of strain. Or we can say, let's say, deformation is same as strain. Depends how, which term do you use. One interesting thing about SPD methods is that, for example, if you have this sample like this, it is this shape. And once it go out, it will be maybe a little bit like this instead of this. It will be just a little bit, how to say, skewed. But the general shape is the same. Like if you don't need this, you can just cut it like this. That is the biggest difference between SPD methods and conventional methods. For example, if you have sample like this, and then you have, let's say, you have this cylinder, and you just upset it, and you get something like this, right? It becomes very, very thin. You will get also, you can get grain refinement up to a certain level, and you may even get, I will show you later, you may even get the same, let's say, hardness, same hardness, but the distinctive feature of SPD that you will have the shape will be almost unchanged. So you can do later whatever you want with this shape. So the shape should not change considerably. So we have plunger that imposes certain pressure or force into the sample and force it to flow throughout this intersection plane. Once it passes this intersection plane, the material will start to shear. You will have plastic deformation. And here it's shows schematically. For example, if you have these, how to say, like squares or circles, depends what you want. Once the material passes this plane, it will be like this. It will be skewed, and it means that it undergo certain deformation. So what is the good thing? What can you do? This is, we call it one pass, right? So you can take the sample and just reinsert it again, and then just press it again and again and again, as much as you want. Of course, there are some limitations with the material, but for example, let me just show you. Okay, I will show you that later. Let me just give you more, how to say, more insight into this methods and the dies. You can see the dies here. What is the good thing about severe plastic deformation? The good thing is that you can just take regular machine or press, just build these dies, and you can do severe plastic deformation. That's not a problem. And it's a good thing about SPD that you can get, how to say, normal size samples. The samples will be not small, like let's say 2 millimeters, and then you cannot do much, right? You can just build normal sample, let's say that with a length of maybe, I don't know, 10 centimeters, and depending how much you want. And here I prepared one animations. I think this is, it's called like physical modeling. So this is not the metal. I think this is made, if I'm correct, this is made of some plastiline. It's like clay, like material. So you can just get some insight about what's going on. So please take a look. Sorry. So that's the thing about this method. You can notice, I'm not sure about the resolution, but you can notice that the squares, actually the squares turned into the rhombus, something like this. Now, I was talking about that you can do multiple, right, passes, and it depends. Once, for example, the samples go out, it depends if you rotate it, if you rotate it, let's say 90 degrees or 180 degrees, or you rotate it in one direction, or you rotate it in another direction. By doing that, you can influence the material properties. So, for example, it has the different name. It says, maybe you can see if I zoom like this. The name are route 8A, route B, route BA, and route C. This is how the scientists agreed on this route, so everybody knows what's going on. And depending how you rotate it, you will get different material properties. So, for example, in this chart, they consider ultimate tensile stress and limit of elasticity. So you can see there are some small difference, and of course they check the hardness. There are some differences, not a lot, but you can notice it. However, in this slide, they consider elongation and area reduction. You can see considerable difference. So depending what you need, what kind of performance, you will get different properties depending what do you need. Okay, I have one chat message. The question from the students who watch the class on YouTube is: effective plastic strain equal to true strain? Well, it should be. I'm not how to say. I think it should be, because I can show you later the definition, but I'm not sure that that they are using these nominal strains. I will check it later just to make sure that it is correct. So one thing to say, just 1 second. One thing to say, SPD can improve the properties of the materials, but in this presentation, I'm going to consider just mechanical properties, because also SPD can influence electrical properties. Electrical properties like conductivity and other things. I'm not an electrical engineer, so unfortunately I cannot talk about this. I will just talk about mechanical properties. And also in every slide I put this this paper or the book where I took the information from, so you can check it later. I will speak with Jaroslav. I can share this presentation in PDF. So if you're interested, I can just send it to him and you can have it. You can check it later. So here, for example, we have the microstructure of nickel. So you can see the initial microstructure and 4-pass route A. So what does it mean? When we check our square with the circle, it was like this. This is like initial 1-pass, then 2nd pass, then 3rd pass, and I guess this is like 4th pass. This is like this. However, this is route A. Where is the route B? Okay, I didn't put it. If we use route C or BC, I'm not 100% sure now. I don't want to make a mistake. What we get in 1-pass, this is initial. This is 1-pass. Sorry, number 1. However, if we rotate it in opposite direction, we will get like this. So we will have these effects, right?
May I ask something? I'm sorry.
Yes, yes.
I don't see any difference between route A, B, and C. What is the difference actually?
Right, B, A, and C, you rotate for 180 degrees, you rotate for 90 degrees. In this case, once you rotate it 90 degrees one way, in other case, you rotate it 90 degrees other way. In route A, you just the position one is go out, you just insert it again, no rotation.
Oh, okay. Yes. Now, yes.
Yes,
Clear.
still don't feel free to ask me, like when I'm live, just interrupt me, no problem at all. It should be
Okay.
better.
I
no?
didn't see the rotation. Yeah, thank you.
Yes. I mean, this is quite, I think this is the most popular SPD method, and it's not hard if you want to do research on SPD. I think if you have some mechanical press in your lab, it should be very easy. You can do like some research or PhD. It's very easy. Okay. Another thing is that SPD is not only used for let's say metals that we get. Let's say how to say. No, I'm not sure with the correct expression. Like the ones you buy from factory, you can also use it for powder. So you can get metallic powder and process it as well. So here's just one paper. You can read it later if you want. And they want to consider how the microstructure of the powder processed material changes throughout the different stages. You have stage 1, stage 2, and stage 3, and they just check. I never did, honestly, I never did research on powder metallurgy, so I'm not familiar if there are more things to consider. But the most, what I read is that the most thing they are interested is if material is porous and not, the shape of the imperfections of the material. And that's why they also invented SPD methods for powder processing. So you can see here, this is like a copper can, and they put pure aluminum particles, and they close this can, and they process it throughout the SPD. And not only that, they add some twisting at the end. They want to make even more, how to say, they want to squeeze material as much as possible. So in this case, they compared the relative density depending on the number of the passes and depends on the processing method. So this is just normal ECAP, and it's called TECAP. So you can see the relative density, let's say in 3 passes, reached almost 100%. Okay, there is one thing I will start to show you now about SPD. We talk later, we say if I reduce the grain size more and more, I will have the better performance. Now, you cannot do it forever. You cannot do it indefinitely. At some point, the defects on the material will be more and more pronounced. So at one point, you will have the drop of the performance. Also, of course, that like we don't know everything about the materials. So for example, I read in one paper, they said that grain refinement, but also grain growth compete with each other. So at some point, the growth of material will start to have more influence, so you might get lower performance. We'll see later. Also here, you can see the microstructure change with ECAP processing. You can see these grains, right? This coarse grain material. And you can see this shear zone, and you can see the microstructure part. Okay, I have to hurry up because I have around 100 something slides. So these are the different features of processing by ECAP. It's usually used for bulk processing. The good thing is, like, we usually compare strain with, let's say, grain size, and also other properties or property improvement. So if I get bigger, more strain, I will have small grains and I will have the properties. So if this is the cross section of the part, depending what I need, but most people say I need even performance. So I want the performance in the entire cross sections to be the same. The good thing is that you will get uniform grain refinement. You can impose the strain uniformly across this cross section, and of course you get uniform distribution of the properties. So it says here strain is evenly distributed, high values of strain. In just one pass you get 1 values. You can do 10 passes. You will see later in my PhD I use other methods. I did 18 passes and so on. Relatively low forces and pressure. ECAP can be easily performed with the standard press and other. The next method is called high pressure torsion. This method was actually invented by Professor Bridgman. And the only thing what he did forget to do was to increase the load. So how this method goes? First, you take the sample. But one thing it's very important to say, usually this sample is not thick. Let's say the thickness is, let's say, 0.8 millimeters, or let's say 1 millimeters. So it's not like, I'm not sure if they did, let's say, with 1 centimeters or 10 centimeters. I'm not familiar with this. So you put this sample between upper and lower die or anvils, and you increase the pressure. So you can also increase from the upper or lower or both, doesn't matter. And then you start rotating one of the dies or both. You can do both. You just need to have the relative movement. So it means that material you have to rotate in opposite manner. So there is one disadvantage with this method, which is unlike ECAP. It says that grain refinement or strain will be the lowest in this point. Why? Because this is the equation for this for the shearing strain. So if the R is 0, so it means that you will not get refinement here. Of course, you get some refinement, but it's not so pronounced that, let's say, the grain refinement and strain like in this area. So 2 pm through T, N is the number of turns, T is the thickness. And depends what you want, you may get different performance. You can do just in just even one rotation, you get considerable strain. We will see it later. So this is, let's say, I just want to show you because it's a good idea. Once this is the disc, right? So this is the disc or the sample that we get. Once we press the sample, it starts to have something like this. So it looks a little bit like this. And you just take the sample and you can cut different specimens that you can use for, let's say, TEM or EBSD, or you can just use, you can just cut some tensile testing sample. You can just test it whatever you want. And here we see the change of the Vickers micro hardness depending on different processing parameters. For example, you can vary the pressure. This is N, it means just 5 rotations, and you vary the pressure. 0.62, 125, increase this one, 0, and of course, like expected, the higher the pressure, the better performance. Again, the difference between, let's say, 2.5 and 6 is not so pronounced. I guess the biggest difference is, let's say, with this. Also, and this is like distance from the center. So let me draw. This is one part of the disc. So this is the center of the disc. So as again we say, the further away from the center, you get the better performance. And in this case, they use the same pressure, 6 gigapascals, and they vary the numbers of turns, and they get similar trend. And of course, you can notice, let's say, some saturation of the performance. It's normal. And in this slide, you can see the microstructure. How does it change when we use different processing parameters? Because we are late, I will not explain it in details. For example, it says here that at 4 millimeters distance from the center, strain of 18. So it's equivalent strain. Is it like something like 2 or 3, and then you get this equation. That's usually what is meant in these equations. So, for example, in one rotation you get strain 18. So if you do 100 rotations, you get 1800 strain, which is really high. No other SPD method can achieve that. The disadvantage is that the samples are thin. So that's the disadvantage, and the strain distribution is not even, it's not equal, so that's not a good thing. You can also cool the dies, you can warm the dies, you can do whatever you want. And here is, let's say, transmission electron microscopy. Here you can see, I'm not familiar if you have the opportunity to work on TEM, but for example, if you don't have this image, if it's not here, then you cannot judge the microstructure. I'm not sure if I'm going to speak. I think I will speak about it later. But let's say in this image proves us that because we have a lot of these rings, it's not like this. It means that grain refinement took place. Also, for example, in this case, they consider the mechanical strength and electrical conductivity. They say usually when you have, let's say, high mechanical properties, electrical conductivity is low, and vice versa. So this is the case. Commercially grade aluminum alloy. This is the name of the alloy. So it means conductivity is good, but performance is low. However, if we process this material using different SPD methods like high pressure torsion or ECAP or high pressure torsion, this material, blah, 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 you can get relatively good strength and relatively good conductivity. So it's like win-win situation. And then also some scientist says, okay, I don't need the whole disk. I will just make a ring. And in this area, I will have, you can say, you will have good performance, you will have even distribution of the properties. And they wanted to check, let's say, aqueous micro hardness, and they check the disk, they check the ring, and again, you have this saturation after a while, let's say after certain strain. Here's the distance from the center. You have here, you can check the change of HV versus the strain. So after the, let's say, strain, I don't know, 45, 50, you get the similar results. That means it maybe makes no sense to further process this material in this way. And they also invented different, it's not high pressure torsion, it's called high pressure sliding and other things. So yeah, because we don't have time. And this is the high pressure torsion and sliding. You can use it not just for disk, you can use it for pipes and tubes. So you see in this case, the distribution of the strain and hardness is not even. So in this case, it's better to use this way. Okay, we don't have so much time. Again, you can see the microstructure. Here, if I'm correct, you can clearly see the grains, the crystal grains. I hope I don't make mistake. But in this case, you get considerable grain refinement. Again, here they wanted to check elongation. So the best, depending on the distance from the center, is it 35 millimeters, 35 to 50, and they just wanted to check certain properties. So again, the main concern about SPD is material properties. Okay, the next method is called repetitive corrugation and straightening. So how does it perform? First, you have one sheet, so it's not used for bulk processing, it's used for sheet processing. And then you introduce this sheet, like again, between those two rolls just to make it more straight. And you make it intentionally, you make like a wave. And after some time, right, you again introduce it between two rolls to make it straight. And that's why it's called repetitive corrugation and straightening. This is continuous method. So like you can just set up this tooling layout so you can get like infinite. You want to, let's say, process 10 kilometers of the sheet. And this is used for, let's say, if you just have one small piece of sheet. So you can just introduce like waviness by this tooling, and later you will strengthen up. And this is the equation for the strain. So this is the bend radius, material thickness, and number of passes. So the key to SPD processing, you don't have to process it in just one pass. You can repeat it many times as you want. Here we just check the microstructure. Again, when you have a lot of these rings, it means you have a lot of grains. Usually, if let's say, if you don't see this image could be, again, let's say it can be also like this. So this is like, I hope I don't make big mistake. if the grains are coarse, you will get something like this. You will not have the rings. So then you know that you get grain refinement. The next method is called multidirectional forging. This method is used for big samples, and usually for the samples that are hard to deform and at a room temperature. So we usually warm it up, let's say this temperature range, 0.1, 0.5 melting temperature, and then you compress it one direction, then you rotate it, and then compress it in another direction, and then rotate it, and then compress it in a third dimension. And the idea is to compress it from the X, Y, and Z axis in directions many times as you want. And finally, you can make, let's say, you can make a rod or bar or something else. So then you can use it for some other processing. The processing temperature is not high. Why? Well, because if the temperature is high, you will have grain growth. We still want to have grain refinement. We want to have smaller grains. So as I said here, it's for usually used for bigger samples, and you can check the microstructure. It says here optical micrograph and SEM micrograph. This is initial microstructure, and this is microstructure after the processing. I don't know how many passes. They also use, I guess, they use some kind of heat treatment and other things. This is unidirectional forming. So in just one direction, just X or just Y or Z, multidirectional forging, X, Y, Z, and as cast, you can see yield stress, and ultimate tensile strength. You get improvements, right? Not big, but, and one good thing, because as I said before, usually when we have, let's say, improvement of hardness, improvement of strength, we usually get the decrease of elongation. However, the good thing about severe plastic deformation that this drop does not have to be considerable. It can be just a little bit, so that elongation is still good, and you can see it here. This is initial material, multidirectional forging, so the value is very close to 29, just maybe 10% or something. The difference is not big. This is the, I guess, ultimate tensile strength and yield strength. This is after water quenching, after heat treatment process. The next two methods, okay, just to say, I think the last time I read about SPD, there are around 70 or more than 100 different SPD methods that the people are just developing like a crazy, including me. So this one is called cyclic extrusion and compression. You get sample like maybe something like this, and then you force it to flow throughout, to get narrow, to flow throughout this channel, and then to expand, and then you compress it. And then you just reverse the direction of the compression, and you can do multiple times. And you can get, let's say, in the one pass, the strain is like this. This is the twist extrusion. You cannot see the tooling here. Once you compress the sample, you just need to design the strain that will flow like this direction. Sorry, not strain, the material will flow this direction. But the thing is that this sample must have hard edges. If it's like circular, nothing will happen. And this method is called Calibrate Rolling. The thing is just put the sample throughout different calibers. So let's say first pass, this is the shape. In second pass, the dimensions are smaller, and you do it many times. And you can see, for example, the distribution of effective strain. So this is the center of the sample. You can see the distribution of the sample depending on the pass. And bad thing about this processing is that strains are lower in the center. Imposed strains are lower in the center and higher at the edges, which is not bad if you want to have some, let's say, surface improvement of the properties. Material improvement in the surface area. In this case, it's not bad. So the thing is, like, you insert the sample between these two rolls, and it's not, the rolls do not have same rotational speed. The one roll, the top and lower rolls have slightly different velocities. So they will impose, for example, if it's like this, let's say rotates faster, this rotates slower. And then intentionally, they will add additional shearing, right? Because then this will go faster, this will go slower. The material will shear like this. And they want to, for example, in this case, they want to compare the properties of the material, properties of the material in, how to say, in this case, it's nominal stress. They want to compare properties depending on the tension and compression tests. In both cases, so this is initial material, in both cases, you get material improvement. That's the thing. And as you can see, the strain here, it's like elongation is very comparable. It's not something like I would say with conventional metal forming, you will get something like this. So the strain will be much lower. Now the strains are pretty much the same. Okay, here they just compare the microstructure and performance between the conventional and SPD methods. I will not focus too much. This is very interesting. Just one table that you can see the change of the microstructure and average grain size. For example, in this case, they have 350 micrometers. In this case, they have 15. In this case, 21, 1.7. So this is usually the range. This is the case by processing by ECAP. Of course, because at the beginning I said that the microstructure should be in this range, 100 to 900 nanometers. Of course, it doesn't have to be, you will not get ultra-fine grains, but you will have considerable grain size reduction. So here in this case, it's almost 100 times. Again, same for this table. In this case, you can get good grain refinement. So 400 micrometers, 300 nanometers, and under here. So let me just give you, or you can just find, okay. Let me just show you what is the thing, why we are so obsessed with the grain size. For example, if you have the grain, let's say this is one crystal grain, so these are the neighboring grains. So we call it big grains, and this is what we call, let's say, small grains. I'll just try to draw it like this. Once the defect appear in one, so this is one crystal grain. Sorry, just want to reduce stabilization. Once some crack or defects appear in here, it can travel throughout the crystal grain very quickly. So you can just go from one side to another side very quickly, and you get crack growth, right? But the problem for the, let's say, some defect or crack, it's very hard to go from one crystal grain to another. It will usually hook on this boundary. So in this case, let's say the length of this crack is maybe, I don't know, 5 centimeters. But if we have smaller grain, then the crack, let's say, propagation is very limited. It can just go from one side, from one side to another, but this length is very small, maybe 5 millimeters. So imagine, like, if you are, I don't know, if you are traveling in Europe. So before, when there was no European Union, at every border you have to stop, like wait 1 or 2 hours. So in this case, you wait here. So imagine these are crystal grains. But in case of Russia, it's very easy. I don't know if the transportation is the same. It's very easy to travel from one side or another. So the smaller the grains, the more, how to say, the more time the crack has to wait. That's why we are so obsessed with these crystal grains. And here they also compare different conventional and other properties. For example, they compare extrusion, they compare friction stir processing with other SPD methods, and that's pretty much it. For example, here they consider elongation. Also, they introduce they're also checking the influence of the strain rate and the influence of the processing temperature. Okay, now we have talk. Okay, I will just finish with this slide and it will make 5 minutes break. In these slides, they're talking about saturation effect. So this is the image from EBSD. I'm not sure if you're familiar with this. This is, let's say, a special microscope. It looks like a little bit like a SEM, but it has additional devices. And it's very good because you can determine the grain size very easily. Transmission electron microscope is very, how to say, it takes time and you must have proficiency to be able to work on this microscope. So this is the initial microscope and each color denotes the grain. You can see the grain. So the zoom, this is 100 micrometers and the strain is 0. If you introduce the, the SPD method is high pressure torsion. If you introduce the strain just 0.5, you will have slight, you can just see that the colors are changing. It means that strains are a little bit different. So it means that grain refinement will take place. After just one strain of 1, at certain parts of the grain, you cannot recognize the initial grain. Once you increase the grain, increase the strain, you will get grain refinement. However, let's say at this point, let's say strain 8, 16, and 32, the grain size, I would say, is totally the same. And by the way, just initial grain size is 17 micrometers. And in this case, maybe, I don't know, less, it's less than 1 micrometer. So it's called saturation effect, and it happens with almost any SPD. Of course, you can introduce some other processing so you can mitigate this effect. But the thing is, you cannot do this grain refinement and strain imposement forever and expect to get like super, like sub-nanometer scale of microstructure. There will be some limits to this process. Okay, so let me just 1 second. Is Yaroslav here or anybody from the? Sorry, anybody from the? So can I make 5-minute pause?
Yes, you can.
Okay, 5-minute pause and see you at in my place is 11:05. Okay, I'm back. So, okay, for the students who asked me this question, if effective plastic strain equal to true strain, it is true, but there are some limitations. Sorry. First, it's only when you have tensile testing. Of this one, it is true, but only before the necking appears. Once the necking starts, then you don't have homogeneous deformation, and it's not true. Also, this is only valid for axis symmetrical parts. So if you have something like, I don't know, something like this, or it's not valid. And also it's valid for homogeneous deformation. So it means, for example, if you have a cylinder upsetting, if you have, I don't know if you're familiar with Rastegar method. The thing is, there is no barreling. Once you compress this sample, it will look like this. But in most cases, it will have this barreling effect. So it is true, but only for, let's say, ideal process. Okay, just to make sure everybody hears me, everything okay? Can you hear me? Everything is okay?
Yes, sorry. Yeah, we can hear you perfectly.
Okay, good. Let's continue. Thanks for the feedback. Okay, so I want you to show you something. One method I invented for SPD processing. It says processing by V-shaped dies. Why V? Because this looks like letter V, right? You have exactly the same two pieces of the dies. They just lie opposite of itself, and you insert this square shape initial. Wait just 1 second. This is the initial shape of the material, and then you compress it, and you get something like rhombic shape alike. And then you take it out. You rotate it for the 90 degrees intentionally, so this axis is longer. And then you compress it again. And you can compress it many times you want, you need, or let's say if the material becomes too hard, or you get some material cracks or something. So it depends on the conditions. So this is the photo of the initial die. We did this, invented this method in our lab in Serbia. Originally, this die was meant to be used to determine material workability, but again, it can be successfully used for SPD processing. So you can see the length of this. This is the length of the initial material, and because there is open, like right, you can see this side of the die is open. Every time you compress the sample, it will be a bit by bit longer and longer and longer. At a certain point, all right, because it becomes longer and longer, this height is getting reduced. So that means that the distance between upper and lower dies is getting smaller and smaller. And finally, it does not make sense to compress it. I did research on low carbon steel, and I compressed it 18 times. So you can see the V-shaped die. That's how it's called, V-shaped die geometry. You can, if you want to, you can also check my publications. You can find the dimensions of this die. And these are the dimensions of the sample. And we intentionally impose a mesh, like a net, on the sample forehead. So we can check the change of this square cell, if you change the shape. So we can measure the strain, we can measure the deformation. As I said, we process low carbon steel. Why? Because it's relatively cheap. At least in Serbia, it's relatively cheap, and it's very easy to deform. And we want to improve the properties of this low carbon steel, so it can have properties of the more expensive and, I would say, higher grade steel. What I needed to do, because initially we didn't know like if this processing is going to be successful or not. So I just bought the material from the workshop and started to deform it, and it cracks after just 2 passes. And because this material was in a form, obtained in a form of like, it's called like bright drawing. it had a lot of residual stress imposed in the sample. So by using this heat treatment, we managed to reduce residual stresses, and then I get 18 passes of processing without any problem. So the heat treatment is very, very important. So this is the microstructure of initial material. This is light microscopy image. This is SEM image. We have two constituents in my case. So if you remember the first, the first, which is slide 56, the one slide I show you here, it has approximately 50-50%. But this is different steel. So in my case, I have 85% of soft phase and 15% of hard phase, and the average grain size was about 19 micrometers. I use this, as I show here, this square will change its shape to look like something, to look something like this. And then I measure these dimensions to calculate the strain distribution at the sample forehead. Again, these measurements are approximately, like it's connected to the question this student asked. You can use these equations only if you have homogeneous deformation. In my case, I knew I wouldn't get homogeneous deformation, but these equations are true for, let's say, these directions. So if you measure the strains in this direction, then it's true, but for others, not so. But again, for me, it was not the most important thing. I just want to get approximate results of the strain distribution. And as I said, I divided the sample forehead on different cells. You see cell number 1, 2, 3, up to 49 cells. So I can check the strain distribution for each cell, and you get the results. For example, in one pass, the highest strain. So this is total strain. So not increment, but total strain. So the highest values of strain I get at the center, 0.39, 0.25, and the lowest strains I get in the edge of the sample. That's how the dye impose the strain. So you see, after each stage, the strains become higher and higher. So some people may ask, okay, what is the high values of strains? What is the low values of strain? Well, it depends on the process, but generally, if I'm correct, the high values are something, let's say, about 1 or 2, and of course, more than 2. So after just 4 stages, we get, let's say, in the sample forehead, we get these values of strain. However, it's very important to say that this is the value at the sample forehead. It's not the value at the very center of the sample. The values here are even higher. This is just because of the strain distribution. So we know that the value here are even higher than in this case. So after 18 stages, the strain distribution at sample forehead, we get, let's say, 3.38 value, and we get the lowest value around this area. And this will be confirmed by our hardness measurement and SEM observations. So you will see we will get the highest grain, the smallest grain and the highest grain refinement at the center region, and the lowest at the peripheral region. I also used some simulations because, of course, we didn't know if this processing is going to be successful or not. So I just run some simulations, and you see I get approximately good results. But of course, the software I use for simulation, I'm not sure if it can include SPD processing effect. So I just think the software thinks this is just regular, like normal conventional metal forming processing. So I guess that's why you get some differences, right? But it's not big difference, so it is okay. So you can see here, I just plotted different, I measured the deformations, is just like rough measurement at the edges and at the center. So here's the average strain increment. And of course, the biggest increment is at the initial upsetting stage. Why? Well, you can see it here because how to say, the taller the sample, the higher the stroke, and you get the higher strain. So that is the only reason, but these are just limitations. And again, I checked this total strain, total average strain at the center and the sample forehead. And this difference will confirm different microstructure and grain size. You will see later. So strain increment at sample forehead and per upsetting stage. Okay, you can see the distribution of effective strain. So you can see at the sample, this is sample forehead. This is center. You can see that the highest values are at the center and of course in this central region. In this outer region, probably because of many effects, the distribution, the strain is not so high. So I did some observations in the different areas. So these are peripheral areas and this is central area. Let me just play, sorry. It's not working. Just 1 second. I'll show you. Okay, I can open the movie. I just want to show you how I cut the sample. So it was something like this. I just cut it in the center and I got something like this. And this is the schematics. So this is the observation of the microstructure by using scanning electron microscope. Usually when you do some, I'm not sure if you are familiar with these microstructural observations, usually you go from the, how to say, the cheapest and the weakest and with the lowest magnification microscope up to the most powerful one. So we already check, once we put this microstructure on light microscopy, we see that we don't see anything. So we switch to SEM. So after first upsetting stage, these images are at the center, and these B and D are peripheral. So you can see after just one upsetting stage, so it means we compress the sample like this, so it became something like this. You can notice just a certain direction of the, just like you can notice that the grains are elongated, nothing else. So you can clearly see the boundaries between the grains, between the ferrite grains and the boundary between pearlite and the ferrite grain. It's not a problem. It's same as its center and the same as in periphery. However, if we do processing in 2 stages, then things become different. So what happened? First, at the periphery, we get because we rotated this sample and rotate it like this, and then compress it like this. So we can say in this stage, the microstructure returned to its original state. Like it becomes like initial microstructure. It doesn't change much. But at the center, so these 2 images, you can notice considerable elongation. And not just that. At some, I don't know if you can see it, and some points, the boundaries between the grains are not so clear. For example, here, you cannot just tell if this is 1 or 2 grains. It's like a little bit dimmed. So it tells you that after just 2 upsetting stage, some grain refinement might happen. So in this case, we check here 8 upsetting stages. Again, A and C are the center, B and D and periphery. In B and D, not considerable change compared to initial one. We just check the pearlite. You can see the breaking of the pearlite. The breaking of the pearlite is good because the more, this is the hard phase. So the more the pearlite breaks, the more even you get, So instead of something like if this is the grain, sorry, and this is the microstructure, so instead of just pearlite, just hard face being like this, it will be better if hard faces are evenly distributed into this matrix and you get better performance. But in center, you cannot, you can see it here, you cannot see what is the grain. At some point, you can see sometimes you can see something, but you're not sure if this is the grain boundary or not. Just check the image below. You can, it does not look like initial microstructure like this, does not look the same. This is the 500 magnification. This is, let's say, 5,000. This is also 500 magnification. And it looks like just, you're just cooking something and you just mix it and just shape it. After 12 upsetting stage, the strain at the center is 3.05. The things are even more pronounced. So this is just 200 magnification. It just look like something. It does not look same compared to initial. For the peripheral regions B and D, you can see the slight, let's say, the slight elongation maybe in this direction. And finally, again, after 12 stages, we also notice at the center some whirlpool. You can see here with the black lines, I noted the material flow. So the more material flows like something like this, so it means that the more, the better grain refinement you should get. Also for the perlite, it stay almost the same, but at some point, you can see the breaking of the perlite, which is good. And this is the final stage, 18 upsetting stages. So you can see considerable elongation, but you cannot see the grains anymore. Here at the peripheral region, you can start to see some dimming. So this is not pronounced anymore compared to before, right? So you get some grain refinement. So I did, because I did my PhD, one part of my PhD in Taiwan and also one part in Serbia, we did it on different microscopes. So this is, let's say, if this is one grain, this is one grain for, let's say, the distribution for our material, the distribution of the atoms is something like this. And this is, let's say, you will see later, I didn't put, okay, I put it later. Yeah, for TEM, you can see that this pattern is totally different. Instead of this, you will get something like this. So instead of dots, you will get rings, and it tells you you get grain refinement. So this is me doing this TEM analysis, just to show you before you do any, we prepared the sample by ion beam processing, and it shows you how you actually, the idea, the goal is to get, the goal is to get sample like this that is like super thin, like you will see later, 80 nanometers. So how you do it? First you put, it says here, protective PT layer, and you dig material like in CAD systems, you make it slimmer and slimmer, and finally you get something like this, and then you put this sample on TEM. And you see here at the top it's 55 and the bottom is 200 nanometers, and then you observe the sample. So this is the initial initial material. You can see these dots. These dots are the same, same as here. So same angle, the distance should be the same. So it's mean this is the material. And this is after second upsetting stage. We knew that we didn't have some grain refinement, but you can see here again, after second upsetting stage, everything stays the same. However, after 4 upsetting stage, you begin these, how to say, uniform distribution of atoms is a little bit disturbed, and you get something like stars or rings. And that's 4 upsetting stage. 6 upsetting stage, I forgot to make the image, sorry. You can see the dimming. And then after 8 upsetting stage, you get something like these star systems like rings, and it tells you you get grain refinement. And again, I did some analysis, and these are the grain. I measured the grain sizes, and it ranged from, I don't know, the highest value, it says 491 nanometers, and the smallest is 140, and the average grain size is 252 nanometers. And initial grain size is 19 micrometers. So it means this processing is success in terms of grain refinement. So this is how it looks like. Not all of the images are the best. The one problem that took us long because we didn't have experience, when you have sample like this, if you put it, because this is like super thin, it's like paper, like it's like, I didn't put it there, you just use something like pen, and because the gravity of the pen is so higher than the gravity of the part will stick to this pen. But also because when you put it in a microscope, you will have magnetic field that will just lose the sample. So if you want to do it and you have some problems, you can just contact me or Yaroslav. I will explain you how to. There are special folders that you can solve these problems. So this is just some graphical report how you can see we can compare upsetting stages, strain, effective strain, and the grain size. So this is 19 micrometers, and this is 252. You can see initial microstructure, how it becomes smaller and smaller. And of course, this is just the start. The next thing is I have to check the material properties. Right? Okay, this is one thing very interesting to say. I'm not sure if you are familiar with the Rastegaev method. Usually, when you have cylinder like this, so this is the top view. Sorry. This is the top view, this is the side view. When you compress it, you will get this barreling effect. However, if you make some small pockets here and put some lubrication here and compress it instead of this, you will get uniform, relatively uniform deformation, and you will get uniform microstructure. So in one case, I compared the hardness of my sample. So this is a sample 444. I will show you. This sample upset 18 times had exactly the same 252 or 242, sorry, Vickers, I forgot. Vickers. Yeah, 243. And this sample, forgot like this, had the same strain. The strain is 2. And also this case, and also my sample, also the strain is 2. Here also strain is 2. And we get the same, exactly the same, almost exactly the same, almost the same hardness. Some people may ask, okay, what's the point? Well, the point is that my sample looks almost like in size, almost like initial sample. It changed the dimensions a little bit, but this sample is like totally flat. You will see later. Also, the microstructure in, let's say, upsetting, so we upset the sample in this direction, is just elongated, right? Just very, very long. So because microstructure is elongated, it means that performance in this direction and this direction is not the same. However, if we check the microstructure in the case of SPD processing, the grains, some grains are elongated and some are not, which is good in terms of performance. So these are the measurements. I think this is for the macro hardness or something, if I'm correct. Yeah, macro hardness. We check the sample, the macro hardness in the 2 regions, center and 6 millimeters from the center. And of course, at the center, we get the higher values. Again, this is like saturation effect. So what does it tell us? So it makes no sense to upset the sample more than 4 times. Okay, maybe in this case, maybe 10 times, but generally the upsetting of in 18 passes stages, it makes no sense. This is also for the micro hardness, and we also check it like in the center, 1 millimeter to the center, up to 5 or 6, the trend is the same. You can say that generally after 4 or 6 times, or depends on the stage, it makes, maybe this is the optimal, the most optimal upsetting stages. This is just the variation of micro hardness depending on the upsetting stage and strain. So this is the center, sorry, so sample 1, so center, and this is periphery. Again, this is also periphery, this is the center. So you can just see the variation. In some cases, it may be like, it can be approximately by linear, in some cases not, but that is general trend. So this is the sample, upset sample. I will go back again. So we just take these samples and we cut it, and we want to see the performance. So from one side of the sample, I machine like super small tensile testing specimens. And on the other side, you will see later, I machine some specimens for the workability. So this is the machine, and these are the results. Of course, the higher the strain, the total upsetting stages, the higher the yield stress and yield strength. This is ultimate flow stress, ultimate tensile stress. So you can see that the optimum is maybe after 4 upsetting stages. Also here. And you can notice one thing here in terms of tensile stress. So this is, tensile testing. The elongation here, the strain is 0.3, but elongation in here drops to, let's say, 0.18, and this case 0.1. So 3 times the reduction of elongation. But we will see later, it's still okay. Now I wanted to check the, sorry, why there is no, there is no, because probably because I inserted later, there is no slide number, sorry. So if you have questions later, I will just read them. I just wanted to check the shape, the appearance of this breaking area after tensile testing, because it also can reveal us many things. First thing, so this is unprocessed material, so right from the factory. So this is, according to the experts that told me, this is considered to be like ductile fracture. So it's not brittle fracture, which is very important, because in this case, in some functions, in some terms, this material can be dangerous because of the brittle fracture. And you can see they call this shape, if I'm correct, cup and cone. So something like this, if I remember correctly, sorry. And then after, once we increase the number of processing stages, we see certain changes. Here, for example, they call this shape of the broken area, they call it Chinese head. Chinese head. You still see the dimples, but for example, you can see the dimples here smaller and the bigger size. And as we increase the number of the processing stages, the dimples become more or less same. The shape is getting almost the same, which is good for the material. And at some point, we also get some like a spiral, if I'm pronounced correctly, spiral shape of the material around here, and you get something like this. But the most important thing is that we get dimples. This means we get ductile fracture. That is really important for us. So I just make this table. I just want to like compare it. Usually we say upsetting stages. What we think is that conventional metal forming can provide you this kind of performance, right? And this kind of fracture, and this is SPD processing. Now the next text is for mobility. For mobility, or some people say workability, is the ability of material to be plastically deformed without any material failure or cracks or something. So if I'm making, let's say, some part, or making, let's say, some parts for a car, or I'm processing car body, I don't want to have some how to say, some cracks or material defect, because that is not okay, and this part cannot be used, right? Also, if you have high formability or high workability or high malleability, so this means, for example, if you have some shape like this, so you can bend it, you can shape it, you can form it more in one stage, in one, let's say, hammer hit or something. Then if material is, let's say, less deformable, if it has less formability, then it means you have to use higher number of operations and smaller strengths. So for us who deals with the metal forming, workability is very important. Also, the higher the formability and workability, the less the processing becomes cheaper, because you have smaller number of operations. So this is the part. In this part, I make this tensile testing, right? You remember tensile testing specimen. In this part, I made samples for the workability testing. So it's just normal cylinder, and it has these lines, these like inscriptions, and we usually expect, when we compress it, we expect some material failure to become active, to appear in this area. It's very rare. I mean, it's unusual for the metal defect to appear, let's say, here. It's usually here, and that's why we use this, so we can measure the strain, and we get these results. So you can see this is the size. So these samples is 10 millimeters tall, and diameter is 8 millimeters. So after upsetting, you get something like this. And I'm not sure if you can see some cracks or something around here. So these are some defects, and we measure the strain, the limit strain. So these are the samples. So this is initial material. S2 means upset 2 times, 4 times, and let's say up to 18 times. And these are the results. Of course, sorry. First, these are the history of the formation. You can see history deformation. You can also measure the triaxiality ratio and effective strain. And this image is actually important for us. We see the dependence of effective limit strain of upsetting stage. Of course, the initial material, the effective strain was limit effective strain was 0.98, but later it drops to something, let's say 0.7 is approximate value. So some people say, yeah, we lose some formability, so we lose some ability to be plastically deformed, but still, this result is still good. Still good. I would say, I'm just paraphrasing, just imagining things, that conventional metal forming, the results would be something like in this range. I'm not sure if I'm right. So this is still good. So it means that we get improvement in terms of micro hardness, ultimate tensile strength, yield stress, but we lose some of the ability of plastic deformation. So just give some conclusions about this method. I'm going to finish maybe in 5 to 10 minutes, so we can have some discussion. So it is said here that upsetting in 18 stages can be carried out. Strain distribution is non-homogeneous. This is a big minus. Maximum values in sample center, and the area maximum is increasing with the number of upsetting stages. Maximum value effective strain in sample forehead is 3.38. Microstructure observations show microstructural change. This is very important, again, because we didn't know at that time if this method is going to be successful or not. And you can see that SPD pronounced SPD effect after 12 upsetting stages, and that's pretty much it. The hardness is the highest at the center, and we get this separation effect. Flow stress and autotensile stress, flow stress and autotensile stress increase with upsetting stages. And C15E kept sufficient for mobility properties even after high number of upsetting stages. And okay, this is the the wrong title. It should be application. So I just talk you here like how much, almost hour and a half, about how this method is good, how it is promising, another thing. But the sad thing is, not many companies, not many factories use this processing. Why? First, you can get grain refinement by other processing. You can get grain refinement also with heat treatment, not just SPD processing. But I just show you why SPD is good. If you already have mechanical, or not mechanical, if you have press, you can easily make samples. So when I start to do research on this, I expected much higher application of this method, but unfortunately that is not true. The people that are giving reports on SPD, the scientists that are dealing with SPD, they say the main reason is lack of information about this SPD. Honestly, I never heard of SPD before I started doing this research, my PhD. But I had the chance to speak with one professor. He works in US. He's also in metal forming area, and he told me what is the reason. It takes time. It is time consuming, and it's in a bit of sense, they say it's complicated. Sometimes they say the companies, for example, he told me like car companies, he didn't say specifically which car company. He says they don't want to do this. They don't want best performance. They don't want the best grain refinement. Sometimes they just want simplest solution, the quickest solution. So that is their how to say strategy. But still, of course, we can the SPD is being used, of course, in many industries. And of course, it's being used in military industry as well. I know one of my friends is working, I don't want to say for which army. They use SPD, but of course, they don't publish these kind of reports. So for example, this is sputtering target. This is used for surface engineering. For example, you put the base material here, and then if I remember correctly, you shoot it with some particle. I'm not sure, I forgot, honestly. It is like ion or electrons or something. And then you eject the material from this, how to say, disk. And then you can put this material in some, you can just transport it and put it in, let's say, in these layers. So yeah, it says here it's used for physical vapor deposition methods. So if you use processing by ECAP, if you use SPD, first, the lifespan is decreased 30%. You get more uniform deposit coating, and you get 75% reduction of the cost. The other thing is these are implants. It's being used. You will see later. I will just show. Okay, I can show it. I can show it now. So this is they plot here the specific strength of the material and innovation probability. For example, automotive is something between aeronautics, biomedical, sports, energy, and the packaging. So it's halfway between. And of course, like for the military and aerospace, we need the highest specific strength. So in this area, SPD is, I guess, is being used extensively. In this area, no, not so much. So like in these like telecommunications and these industries, not much. So again, George, just to say again, remember this, biomedical. So these are medical implants. And there is one, I didn't put it, sorry, I don't have it here. One interesting thing, you can also make implants for if somebody breaks an arm, or you can use it just for other purposes. One of the things, you use it for teeth, for tooth, right? For the dentistry. And for example, this is the implant for the adults, but you cannot use this implant for children. Why? Because of the shape, because of the size. The size of the head and the skull of the babies and the children is not the same as grown-ups. However, and of course, yeah, just want to say this, these implants must have certain mechanical properties, right? But if you use if you make material stronger by SPD, you can just reduce the size and have the same ultimate tensile strength and yield strength. So you, in between these two, let's say this is processing by SPD, this is conventional metal forming, the properties are exactly the same. But the good thing is that the size is smaller, and now you can use it further. Other thing, if you reduce the size of the implant, when the surgeon and the doctor, or what is the proper employment, is performing the surgery, if the implant is smaller, then the doctor does not need to cut, or how to say, to remove the tissue of your body so much. So if smaller the implant, less working time, less intrusion into your body, and also quicker recovery. So that is also one of the things. So generally, the smaller the implants, the better. But of course, we need to keep it the same. We need to keep the same mechanical properties. So it says here the acceptance by industry is slow. So sport, medical, mechanical, aviation, and other industries, titanium implants. This is turbine blade. Of course, you don't have to use just severe plastic deformation alone. You can use it with any other, like you can combine SPD and conventional, or SPD with machining and other processing technologies. So in this case, it's used for microforming. So it says micro bulge sheet. So this is conventional grade material, and this is ultrafine grain material obtained by didn't say which process. So when you make these small parts, you get this, it's called orange peel effect. But when you use small grains, the material with smaller grains, this effect is less pronounced, and so the shape looks better. Also, we need to say something about materials. Aluminum, this is the study I did, let's say, sorry, this is the year, and this is the number of scientific papers. But generally, the trend is the same. Aluminum and its alloys are being the material that is mostly being investigated. Then it's steel, copper, titanium, nickel, pure iron, zinc, and other alloys. So you can see here the number. I can show you here the number of the research papers that deal with SPD is increasing year by year. So in 2012, it was 600 papers. In 2020, it was 825. I would guess it will be even higher, but because of coronavirus, there are some difficulties, right, for the scientists, and generally for everybody, not just the scientists. So these are the most famous scientists that deal with this. I would say Ruslan Maliev is the most famous one. Then we have, he's from Russia. Then we have Terence Langdon from, I think he's correct, either UK or Australia, sorry, I don't know. Then Zenji Horita from Japan, Professor Pippin, I think he's from Austria or something, and others. Generally, the scientists from SSR, from Soviet Union and Russian Federation are the most numerous one that deal with this subject. So that's pretty much it. I'm right on time. We have 10 minutes for discussion. So please, I'm curious if you have some questions.
Yes, maybe it's a little bit of a basic question, but can it also happen when you plastically deform a material too much that it breaks? Because like intuitively, I would kind of expect if you like push it through this tube that is curved, that maybe it crumbles also a little bit, or does that never happen?
Yes, your question is very good, because I forget to say one very important thing. Thank you for asking this question. So first, Jenny, I can ask you or other things. If we have the same shape material, in one case we compress it, in other case we tensile testing. So let me just write, sorry. If I have like this shape, in one case I stretch it, in other case I compress it. What do you think which processing direction you can impose the higher strain, in upsetting or tensile testing? Which the force, how to say, what would be the higher force in which case? In this case or in this case, and why? Can somebody say something? Okay, the material can withstand much higher load in terms of compression. Did you wanted to say something?
Yeah, no, I mean, yeah, that sounds kind of intuitively when you say it like this, yeah.
Yes, compression. Why? Because every material, initial materials have some small defects. It's normal, like it's normal thing. If you tensile test it, sorry, if you, how to say, you stretch it, these cracks will become higher and higher, and they will start to connect with each other, and finally material will break. But in other case, if you compress it, if you have some small, let's say, voids, some small cracks or something, if you compress it, it will just close down. So I just forgot to say, SPD is designed to favor the compression. So especially like if you check my processing here, my processing method, you can see this is based on compression. So that's why if you study metal forming, you know that high hydrostatic pressure condition will yield higher strains. So if you keep metal, how to say, if you compress it, if you keep it together, then there is a lower chance to be broken. But as again, of course, there is a limit to any method. You just have to design it. You need to try it. You need to use simulations.
Okay. Yeah. Thank you very much.
Okay. Anybody else?
Hello.
No. Okay.
Hello.
Yes. Pavan.
So,
yes. You can.
Yeah.
You
Yeah.
can ask.
I have been watching in YouTube, so I just got a question. So can you open the slide number 65?
Yes. 65. What is the slide 65? Sorry, 1 second. Okay, this one.
I mean, regarding simulations, like generally the effective strain distribution for materials will be like less than 1, right?
But wait, this no. This is after 18 times. Okay, I'm sorry, I forgot to write it. 18 upsetting stages.
Like actually, right.
Actually,
right now I'm doing my master degree in Taiwan regarding metal forming process. So in my case, I'm doing same metal extrusion, double extrusion in Z-axis and minus Z-axis. So like that, I mean, for aluminum, the effective strain will be like less than 0.5 or 0.6.
Yes,
that is strain.
Yes. But I get in one pass, sorry, at the center, I get something like 0.4.
Yeah.
Yes, but this is after 18 passes, and I think this is not true. Because I couldn't measure it. I'm not 100% sure. What I wanted to just want to check distribution. That was my main concern. I cannot guarantee this value is right, but for the sample forehead, after 18 upsetting stages, I get something 3.38.
Like, is it? I mean, can we judge that, like, since the strain is very low for materials, this is good or not? Like,
this is good. This is good for this shape and this material, because I told you I had. Let me just switch to another slide. Sorry. I had cylinders, and if I set it like this, like it's like almost the maximum, I get around strain around 2, which is low. I mean, it's not low, but that's the maximum. You cannot compress. This is like this is like 20 millimeters, and this is like maybe 2 or 3 millimeters. I cannot do further.
Yeah. So it does not. So it does not depend on the value.
No. It's
I
not.
mean,
It's for specific for each process and each material.
oh, okay.
So, for
I
example,
mean, if the strain distribution is very good in, I mean, though the strain is very higher, but the strain distribution is very good in the end of the product.
well, what is the problem? If I want to have SPD, and usually in this area, I don't have SPD effect. The strain is relatively low. You can see one. I mean, it's not low, but it's lower. So what can I do? I can take this sample and just machine this part with a higher strain, and then make something out of it. So that is one of the solutions. Or I can just scale up. I can just increase, just make the sample bigger, and then I will get the higher area.
Yeah. So the reason why I asked it, but in my case, I'm using aluminum 6061. So the effective plastic strain is high, but if I compare to the graph, the strain is high, but my strain distribution is very good. Actually, I'm manufacturing a gear, but my strain distribution is very good. I think only at 2 or 3 points, I mean, like only at 2 or 3 points, my strain is very high, and overall strain is like less than the graph. So I think it is good, right?
Yeah. In your case, it's good. Here it's just all right. But again, I just say I will just make this part for me that's useful part, and I will just discard the rest of the part.
Okay. Thank you so much.
Okay. Please let me know if you have more questions. Okay, we have like less than 2 minutes.
Just maybe one, again, quite basic questions. Right in the beginning, in slide 7, I think it was, with a picture of the titanium crystal. I think for some crystals, you can already see that they just grow in the same direction, roughly. Why is that? Like that they are not completely random, but those next to each other kind of go in the same direction.
I'm not really familiar with this, but I just use this illustration and just to show you that crystals grains can be big, like you can see it with your own eyes. So that was the main idea. But I'm not sure how do they make this sample. No, I'm not really sure. I suspect maybe they use some casting, but I don't want to make mistake.
Okay, yeah, I see. Thank you.
Okay, so that's pretty much it. Thank you everyone for your attention. I hope you had a nice insight about severe plastic deformation. If you have some questions, you may, actually I wasn't smart enough, so I didn't leave my email. Let me just write it quickly. My email is like this. Sorry. marko.vilotic@gmail.com. You may contact me, or you can ask Jaroslav. I think he's the organizer. I'm thinking about publishing this presentation into PDF, so he can send it to you as well. So yeah, just hope you had a good time and that you get some insight about severe plastic deformation, because I think it's very interesting, and it deserves a lot of attention. But I guess industry knows what is the best for them. Okay, thank you for your time.
Hvala, bilo je jako zanimljivo predavanje.
Hvala.
Thank you very much. It was very interesting. Have a nice day. Bye-bye.
Okay, thank you everybody. See you. Bye-bye.
Pozdrav.